Hello everyone!
Welcome to this presentation on the deflection of beams using Macaulay's method.
Beam deflection is a crucial concept in structural engineering, influencing the design and safety of structures.
Today, we will explore Macaulay's method, its application, and walk through a couple of examples to illustrate how it works.
In structural engineering, deflection is the movement of a point or beam away from its original location due to stresses and loads acting on the member.
It is also known as displacement, and it can be caused by externally applied loads, the weight of the building itself, or the gravitational pull.
Deflection can happen in beams, trusses, frames, and almost any other construction.
For the concept, first, let's understand what beam deflection is. Beam deflection refers to the displacement of a structural element under load. When a beam is subjected to forces, it bends, causing its shape to change. The amount of deflection is critical to ensure the structural integrity of buildings, bridges, and other constructions. What is Macaulay's method? The concept of deflection of beams using Macaulay's method involves a systematic approach to determine the deflection and slope of beams subjected to various loads. This method is particularly useful for beams with distributed loads or varying loads conditions. Here are some key aspects of Macaulay's method. This method is named after Colin Macaulay, a British engineer and mathematician who developed a systematic approach in the early 20th century. In his 1908 paper, The Deflection of Beams, he introduced a more straightforward method for calculating beams' deflections, especially for those under complex loading scenarios. His technique used a piecewise definition for bending moments, making it easier for engineers to manage different load conditions. This approach proved especially effective for beams experiencing distributed loads, point loads, and various support types.
Macaulay's equation. The method uses the differential equation of the elastic curve, which relates the deflection of a beam to the bending moment. The equation is generally expressed as the second derivative of the vertical deflection y with respect to the horizontal position x is equal to the bending moment mx divided by the product of the material's Young's modulus E and the beam's second moment of area, where y is the deflection, mx is the bending moment as a function of position x, E is the modulus of elasticity, I is the moment of inertia of the beam cross-section. Macaulay's method is particularly advantageous for complex loading scenarios because it simplifies the analysis of beam deflection and slope without needing to derive multiple equations for different sections. Deflection differential equation in simple form. The second derivative of deflection y with respect to the length of the beam x gives the curvature, and multiplying by EI provides the internal moment needed to resist the curvature. First integration. EI times the first derivative of y with respect to x is equal to the bending moment m times a small change in x plus a constant c1. E is the modulus of elasticity, I is the moment of inertia of the beam's cross-section, y is the deflection of the beam, m is the bending moment, dx represents an infinitesimal change in the length along the beam, and c1 is a constant of integration. Second integration. EI times the first derivative of y with respect to x is equal to the bending moment m multiplied by an infinitesimal change in x squared plus the product of constants c1 and c2. Additional information: if the beam has support, the deflection is 0. If the beam is a cantilever, the deflection and rotation are 0.
Steps in Macaulay's method. The steps in Macaulay's method can be summarized as follows. First, determine the reactions. Use static equilibrium to find reactions at support. Second is define the load distribution. Break down the beam into segments based on loading conditions. Third, write the moment equation. For each segment, write the moment equation using Macaulay's notation. This involves using the Macaulay's brackets to handle varying load conditions. Fourth, integrate the moment equation. Integrate the moment equation to find the slope and then integrate again to find the deflection. Lastly, apply boundary conditions. Use known deflection and slope conditions to solve for constants in the equations.
Let's consider an example of a simply supported beam with a span of length 6 meters. It has a pin support at one end and a roller support at the other. The beam carries a uniform distributed load of 1 kN per meter across its lengths. Use Macaulay's method for the simply supported beam loaded as shown in the figure to determine the equation of slope and the deflection of the beam. In solving the reactions, you just have to follow these steps. With the given problem, we're now going to solve the problem. First, we need to determine the reactions at the support using static equilibrium. Let's first get the total load due to the distributed load between C and D, which is 1 kN per meter times the distance of it, which is 2 meter, is equals to 2 kN. Now, let's get the vertical load acting on a beam at A, using moment at E first. The summation of moment at E equals 0, which is going to be AY times the total length of the beam, which is 6 meters, minus the first force is 6 kN times its distance, which is 5 meter, minus the second force 4 kN times on its distance 3 meters, minus on the distributed load 2 kN times its distance 2 meters equals 0, which is going to be the AY is equals to 7.67 kN. Lastly, we're going to find the reaction at E, using moment at A this time. The summation of moment at A equals 0 is equals to negative dy times 6 plus 6 times 1 plus 4 times 3 plus 2 times 4 equals 0, which is going to be dy equals to 4.33 kN. Step 2. Load distribution. The load is uniformly distributed along the length of the beam. We can express it as a function of x, where 0 less than or equal to x less than or equal to L. The load distribution is comprised of point loads at B and C, and a uniform distributed load from C to D. We can express the total loading on segments AB, BC, CD, and DE. But for this example, we are going to solve the moment at segment DE. Step 3. Moment equation. The moment about point A at a distance x is given by, for a moment at segment DE, summation of moment DE equals 0 equals 7.67 times x minus 6 times x minus 1 minus 4 times x minus 3 minus 2 times x minus 5. Step 4. Integrate the moment equation. Now, we integrate the moment equation. For first working equation is this, which is we're going to change the parentheses into bracket only. Next, we are going to integrate it. First integral is this. After the first integral, next is second integral. It should be like this. After integration, we will find expressions for the slope and deflections. Step 5. Apply boundary conditions. Next, we apply the boundary conditions at the supports to determine the constants of integration at point A and E. The deflection will be 0. Solving this will yield the deflection at point D. Step 6. slope and deflection. For the final last step, we are going to solve for the equation of slope and deflection of the beam. To write the equation of the slope, the equation is the first integral, and just substitute the value of the C1. To write the equation of deflection, the deflection equation is the second integral, and just substitute the value of C1. And there you have it. We finally got the equation for the slope and deflection at the beam.
To recap, we explored beam deflection and Macaulay's method, covering the steps involved and providing an example with a simply supported beam with a pin support and roller support.
Understanding beam deflection is vital in ensuring the safety and integrity of structures.
Macaulay's method is an invaluable tool for engineers to calculate deflections accurately.
Thank you for joining us in this presentation.
Bye!